That is why the galvanometer will give deflection to the right direction at the time of break of circuit. Let us see again and visualize the effect. Right now only one coil is given supply. So due to that, this the secondary coil is induced current, but that induced current is in the opposite direction as per the Lenz law, right? And the galvanometer deflection you can see. Okay, we will see another case of mutual inductance. See, this one is a study practical for the step down transformer or step up transformer study. See, as we know that the transformer is working on the principle of electromagnetic induction. That is, when the current in the one circuit changes, an induced current is set up in the neighboring circuit. It consists of two coils, primary and secondary. These coils are insulated from each other and wound over the same core. So in order to avoid the eddy currents, the core is laminated. The alternating electrical energy is supplied to the primary coil. That is, this one is our primary coil. The output electrical energy is drawn from the second coil. That is, this coil we will get the output. So in the step down transformer, the primary coil is consist of a large number of turns of the fine insulated copper wire, and the secondary coil will consist a few turns that are thick insulated copper wire. In step up transformer, the primary coil consists of few turns of thick insulated copper wire, and secondary coil consists of large number of turns of fine insulated copper wire. So in this type of transformer, the core is largely surrounded by the coils. This one is the core. The transformer makes the use of Faraday's law and ferromagnetic properties of iron core of efficiently raise of lower AC voltage. So now we will see that transformer cannot increase the power, so that if the voltage is raised, the current is proportionally lower and vice versa. Now what we will do, we are having 5 different number of turns. We will take in primary as a 200 turn and secondary as a 800 turn. Now we will give the power to the first coil. So what will happen? Due to that coil, there will be a mutual inductance that will be created in the secondary coil. Right now in AC volt primary side it is 6 volt, but in secondary side you are getting 24 volt. Why? Because of the transformer action that is done in this two coil. So now we will see how the transformer is actually doing the step up operation or step down. Let us see the step down operation also. This one is called the step up operation because in the secondary side we are getting 24 volt. In the primary side the voltage is only 6 volt. Here the voltage are getting 4 times lower. Why? Because there is a certain coefficient. Due to that coefficient it is getting increase or it is getting decrease. So to know more about the mutual inductance and their effect, we will find out one coefficient. That coefficient is called the coefficient of mutual inductance or mutual induction. It is denoted by capital M. We will now deduce an expression for the coefficient of mutual inductors in the terms of dimensions of the two coil. Let us assume that the flux in the first coil phi 1 is equal to N2 into I1 divided by L divided by mu naught mu r into a Weber. What is this L divided by mu naught mu r into a? It is a reluctance. And what is this N2 into I? It is the MMF or the magnetomotive force of the coil, right? Okay, so we can write flux per ampere is equal to phi 1 divided by I1. So what is my phi 1? Phi 1 is equal to N2 I1 divided by L divided by mu naught mu r into A. So I have just put up this value in this equation. Okay, now assuming that the whole of the flux that is linked with the other coil, if we are having two coil, so whole this flux will link with the another coil having N2 turn. So due to this flux per ampere in the first coil, what will happen? We can say that mutual inductance M will be created as M is equal to N2 into I1 divided by I1. So as we know that the equation can be rewritten again, as we know the value of I1 and we also know the value of phi1. So putting those value, we will get N2 into N1 divided by L divided by mu naught mu r into A. Again, if we simplify it, then mu naught mu r can be put at the numerator. So it will be mu naught mu r into A into N1 N2 divided by L Henry. Or another way, another word notation, we can write M is equal to N1 into N2 divided by L divided by mu naught mu r into A. So N1 and N2 are the number of turns of primary winding and the secondary winding, or primary coil and secondary coil. And what is this? L divided by mu naught mu r into A? It is a reluctance. So in general, I can write M is equal to N1 into N2 divided by S Henry. So in any case, if I want to find out the mutual inductance of a circuit, then I can find by putting value, that is M is equal to N1 into N2 divided by S. Okay, we will now see the coefficient of coupling. Okay, the coupling between the coils can be increased by wrapping the two coils around a core. The fraction of the magnetic field that is coupled is referred as the coupling coefficient. See, in this left hand figure, you can see that the two loosely coupled coils are put up, and in the right hand figure, you can see that the two coils on a ferromagnetic core are put up. So what will happen if we are putting this type of inductive coil in the ferromagnetic core or in the loosely environment? What will happen? The fraction of the magnetic field will be coupled, and that is called the coupling coefficient. So this coupling is particularly very much important in the transformer study. The arrangement below given is a coupling coefficient that is very close to 1. See, you can see here in this figure that a coil of a ferrite toroid is put up, and this figure, the coils are wounded on a laminated steel core. As the coupling coefficient in between the two winding is 1, so what will happen? That it will follow the equation that is used in the transformer. So the most transformer approximate to ideal component, that is, they have the coupling coefficient is equal to 1. For such a device, when they are unloaded, they will behave as their behavior is determined by the turns ratio. That means for alternating voltage, if we are connecting this type of two coil, that is N1 and N2, and we are connecting N1 with the certain voltage V1, so what will happen? Due to this, there will be a mutual inductance between the two coil. So what will happen? That this voltage will get transferred to the another coil, or you can say that the voltage will get induced in the another coil. So if I want to find out V2, then as the coupling coefficient is equal to 1, so which equation I can use? I can directly use this equation, that is V2 divided by V1 is equal to N2 divided by N1. Okay, when we are using transformer with a resistive load, the current will flows in the secondary. So this current is itself produces a magnetic flux which opposite that produced by the primary. Thus the current in the secondary will reduce the output voltage. So for an ideal transformer, we can say V1 I1 is equal to V2 into I2. But as the coupling coefficient is only 1 in the ideal transformer, So in another case, if we are putting any number of coil, we will not get this relation V1I1 is equal to V2I2. But in the case of transformer with a resistive load, this type of relation is generally achieved. Okay, we will now see the coefficient of coupling. So to study about the coefficient of coupling, we will consider two magnetically coupled coil. One is having name as A and another one is having name as a B. Each coil is having certain number of turns. Let us say that first coil is having number of turn is equal to N1 and second turn is having number of turn is equal to N2. And we will find out their respective individual coefficient or the self inductance. So what will be the self inductance of coil 1? It will be denoted by L1. So L1 is equal to N1 divided by reluctance. And similarly L2 for coil 2, it will be L2 is equal to N2 square divided by reluctance. Reluctance is equal to L divided by mu naught mu r into A. It is similar to the resistance in the electrical circuit, right? So the flux Phi1, that is in the produced in the coil 1 due to the current I, the flux will be flux Phi1 is equal to N1 I1 divided by L divided by mu naught mu r into A. Suppose a fraction Kf of this flux, that is K K1 Phi1 is multiplied with N2 divided by I1, where we can say that K1 is less than or equal to 1. Or another way, simply assume that K is the coefficient that is denoted by mutual inductance M is equal to K1 Phi1 into N2 divided by I1. Or we can simply say that N2 is equal to K into Phi1, right? Agree? So substituting this value in the equation, that is in the Phi1, we can write M is equal to K1 into N1 N2 divided by reluctance. So similarly, in the coil 2, flux 2, that is Phi 2, will produce in the flux density due to I2 ampere in the Phi 2, that is flux Phi 2 is equal to N2 into I2 divided by reluctance. Suppose a fraction K2 of this flux, that is K2 Phi 2, is linked with the coil A. So what will happen? The mutual inductance M will be, obviously we have to put over here, that is K2 Phi 2 into N1 divided by I2. Let us rearrange again. So what will happen? M is equal to K2 into N1 N2 divided by reluctance. So we have obtained two different equations for the different coil. So multiplying these two equations, that is 1 and 2, we get M square, that is at the left hand side we will get M into M, so it will be M square. In the right hand side it will be, there are two coefficients K1 and K2, so they will again multiply, and same way the flux will also get multiplied, that is N1 square divided by L divided by mu naught mu r into A. This one is the reluctance of a first coil. Similarly this one is the reluctance of a second coil. So we will get one relation, that M square is equal to K1 K2 L1 L2. So putting under root K1 K2 is equal to K, we will get one relation, that is here if we are putting K1 K2 on behalf of K1 K2, if we are putting K under root K, so it will be M is the mutual inductance is equal to K under root L1 L2. But here in this theory we are interested to find out the coupling coefficient. So what is our coupling coefficient? It is K. K is equal to M divided by L1 into L2. So this one is the formula that you have to remember for the solving of numericals. Okay, so the constant K is called the coefficient of coupling. It may be defined is the ratio of mutual inductance actually present between the two coils to the maximum possible values. That means here you can write K is equal to ratio of mutual inductance divided by the total inductance in between the two coils, right? So if the flux due to one coil is completely linked with the other, then the value of K will be 1, that is, it will be unity. In that case we can say that the two coils are tightly coupled, right? But if the flux of one coil does not at all link with the other, then the value of K will be 0. So it is, we can say that, magnetically isolated. So here now you should understand in your mind that you are having two coil, and if your coefficient of coupling is 1, then you can say that these two coils are tightly coupled. That means here the whole EMF flux can be transferred or linked with the other coils. But if the value of K is 0, then you can say that they are not magnetically isolated. Okay, now we will see the series parallel combination of the inductance. After seeing the series parallel combination of inductance, we will try to solve some numericals, and we will also see that how the coupling coefficient can be used to find out the series and parallel combination of the inductance. See, inductors can be connected in series or in parallel. Likewise, we are connecting the resistors in series or in parallel. So when several inductors are connected together, their effective inductance can be calculated in the same way for the resistor. But the provided thing is that you should keep in mind that they are not linked magnetically. What is mean by this? That they are not magnetically linked. Magnetically linked that means that the value of K is isolated, that is 0. Okay, so in this one is the inductor symbol if we are connecting them in series. So if they are not magnetically linked with each other, then we can simply write L1 plus L2. But as we know from the Faraday's laws and some other experiments, that the coil will not always link magnetically. They will always link with the magnetically with the each